Chapter 8 deals with molecules, materials, and metals. The first part has to do with the intermolecular forces that hold molecules together in the liquid or solid state. So we're going to look at a number of molecules and determine what types of intermolecular attractions are present in these molecules. To do this, you have to know the shape, and we begin then by assigning the appropriate Lewis structure for each molecule. Now there's going to be three types of intermolecular attractions that we will consider. We will consider, first of all, dipole-dipole forces, which are present anytime you have a polar molecule, dipole-dipole forces. Secondly, London dispersion forces. And those are present in all molecules. They are the strongest intermolecular attractions if you have a nonpolar molecule. And the third type will be hydrogen bonding. And you know that you have a hydrogen bond, which is an intermolecular attraction, if inside of a molecule you have hydrogen covalently attached to fluorine or to oxygen or to nitrogen. If hydrogen is attached to one of those atoms, then you will have hydrogen bonding between the molecules. So let's take a look at this. So we're going to first of all draw the Lewis structures and then determine the shape. Sulfur dioxide, sulfur has 6 valence electrons. Each oxygen has 6. 6 times 2, that's 18 electrons. So when we draw the Lewis structure, 2, 4, complete the outer octet, 6, 8, 10, 12, 14, 16. Put the leftovers on the central atom, 18. Give the central atom an octet with a double bond, so we put it there. Now when we count the number of electron groups around this atom, there are 3 groups of electrons, and therefore the electron group geometry would be trigonal planar, but the molecular geometry is going to be bent. It's bent with an angle of about 120 degrees. Why 120 degrees? Because there's 3 groups, and the way that 3 groups can get as far apart from each other as possible is with 120 degrees. Now sulfur is more electron positive, and each oxygen is more electronegative. And so this is a polar molecule. This is a polar molecule. And since it is a polar molecule, we know that the types of intermolecular attractions that are present include the dipole-dipole forces, and of course, London dispersion forces are present in all of these. So, and the London dispersion forces. And we know this because this is a polar molecule. Sulfur dichloride, we have to do the same thing. We have to draw the Lewis structure. Sulfur has 6. Each chlorine has 7. That's a total of 20 electrons. When we draw this Lewis structure, sulfur is the central atom attached to 2 chlorines. 2, 4, we complete the outer octet, 6, 8, 10, 12, 14, 16. We put the leftover electrons on the central atom, 18, 20. Now there are 4 groups of electrons around the central atom, 1, 2, 3, 4, and since there's 4, the electron group geometry would be tetrahedral. And when the atoms attach then, they will be bent. This will be another bent molecule, but this time the bond angle is approximately 109.5. This is bent approximately 109.5. Now, why 109.5? Because there's 4 groups of electrons around the central atom, 1, 2, 3, 4. And the way that they can get as far apart from each other as possible is tetrahedral, 109.5. Now, once again, chlorine is more electronegative than sulfur, so we have partial negatives here, partial positives here. They don't cancel each other out, and so therefore this is a polar molecule. And so sulfur dichloride also has dipole-dipole forces and London dispersion forces. It also has dipole-dipole forces and London dispersion forces. Just put bullet points here. Next, we'll look at sulfur tetrafluoride. The way to determine the types of intermolecular forces is to determine the shape and determine if the molecule is polar or not. Sulfur tetrafluoride, sulfur has 6. Each fluorine has 7. That's 28, and 6 is 34 electrons. When we draw the Lewis structure, we'll have 2, 4, 6, 8 complete the octet on outer atoms, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons, but there's still 2 more electrons, 36. We put them on the central atom. Now there are 5 groups of electrons, 1, 2, 3, 4, 5 around the central atom. And the perfect shape that goes with 5 groups of electrons is trigonal bipyramidal. which we could draw like this. But remember, there's one lone pair of electrons. Where do the lone pair of electrons go? They have to go in an equatorial position. That leaves the fluorines here, 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 and here. And so what is the shape of this molecule? This molecule is seesaw. This has a seesaw shape. And is this one of the perfectly symmetric structures? And no, it's not. Seesaw is not perfectly symmetric. There's a pair of electrons on this side. There's not a pair balancing them on the other side. Therefore, this is also a polar molecule. And so this molecule also has dipole-dipole forces and London dispersion forces. So London dispersion forces are present in all liquids and solids of molecules. They are temporary induced dipoles, but because this is a polar molecule, it also has dipole-dipole forces. H3PO4. Now, when we do the Lewis structure for this, each hydrogen has 1, so 3 times 1. Phosphorus has 5. Each oxygen has 6. So 24 and 5 is 29, and 3 is 32 electrons. Okay. So the phosphorus is the central atom attached to 4 oxygens, 2, 4, 6, 8. And then the 3 hydrogens are each attached to different oxygens, 10, 12, 14. So there's 14 electrons. Now complete the octets on outer atoms. Well, the hydrogens each have an octet. Remember, for hydrogen, an octet is 2. So we'll go 16, 18, 20. Now we'll complete the octets on these oxygens, 22, 24, 26, 28, 30, 32 electrons. That's all 32 electrons. So this is a valid Lewis structure for this molecule. Now, as we look at this molecule, this has a polarized hydrogen. A polarized hydrogen is a hydrogen covalently attached to either fluorine, oxygen, or nitrogen. That's what I drew up here. Since fluorine is so electronegative, this is partial plus, partial minus. So this hydrogen is very polarized. This is partial plus, partial minus. This hydrogen is very polarized. I inadvertently wrote nitrogen first. Doesn't matter what you write first. I can write H, N, and this hydrogen is partial plus, and nitrogen is partial minus. Each hydrogen here is polarized, and it's attached to a very electronegative atom. So this is a polarized hydrogen attached to an electronegative atom. It will hydrogen bond to another molecule of itself. It's not a perfectly symmetric shape. I have an oxygen up here, and I don't have, I have OHs down here. And so the strongest type of intermolecular attractions present in this one will be hydrogen bonds. It's a polar molecule, so it also has dipole-dipole forces. And there are London dispersion forces. So this has all 3 types of intermolecular attractions in the pure state when we have pure phosphoric acid. Okay, now the next molecules are organic molecules, and we can use the shortcut for drawing the Lewis structures of organic molecules as we look at them. The shortcut is that carbon has 4 bonds. Each halogen, chlorine as a halogen, will have 1 bond. So the Lewis structure simply looks like this. And we could complete the octets on outer atoms, but that's really all we need to know. Around the central atom, there are 4 groups of electrons, which makes this tetrahedral. So since this is tetrahedral, I can draw it like this. A straight line represents a bond in the plane, the wedge, a bond coming out of the plane, parallel dashed lines, a bond going back. Now, if I were to look at this as a solid, so let's connect each of the chlorines. This is a tetrahedral shape which is perfectly symmetric. Each chlorine is more electronegative than carbon, so I have partial negative at the point or at the apex, at every apex of this tetrahedron. The carbon right dead center in the middle is partial positive. This is overall non-polar because all the positives, they're symmetrically oriented around that. All of the negative charges, rather, are symmetrically oriented around that positive charge. So tetrahedral is one of those perfect shapes, and that since it's a perfectly symmetric shape, it's non-polar. And so therefore, the only type of intermolecular attractions that's present in carbon tetrachloride will be London dispersion forces. because this is a nonpolar molecule. How do you know if something's nonpolar? If it's a perfectly symmetric molecule. Now, if I replace this chlorine with a hydrogen to get chloroform, so I don't have to draw this again, the Lewis structure is going to look the same, so I'm going to just replace the top chlorine with a hydrogen. I could put the chlorine anywhere. It doesn't matter because a tetrahedron, it would look the same. It's just easier for us to see if I put the hydrogen on top. So when I connect these again so that I can see this as a solid, now we have a partial negative at each corner of the base, but carbon is more electronegative than hydrogen, so this is partial positive. This is partial negative here. Each of these is partial negative. This is a polar molecule. The bottom is more negative, the top is more positive. A polar molecule is one that has an unequal distribution of charge, that has a positive end and a negative end. So this is polar. Even though it's tetrahedral, it's not enough for something to be tetrahedral in order to be nonpolar. It must be what I like to call a perfectly symmetric tetrahedral. And so this is polar. And so the types of intermolecular attractions present in chloroform include dipole-dipole forces. Anytime you have a polar molecule, you have dipole-dipole forces and London dispersion forces. Now the next few, I don't think I'm going to draw the entire Lewis structure for the next few. Well, I think I will draw it. I'll just draw it this way. The Lewis structure, each carbon has 4 bonds. So this carbon is attached to 3 hydrogens, 1, 2, 3, and to the carbon that follows. So the CH2, this carbon is attached to the carbon in front and 2 hydrogens. Now you remember this because carbon has 4 bonds. This carbon is attached to the oxygen, which is attached to a hydrogen, and when oxygen has 2 bonds, there will be 2 lone pairs of electrons on it. Now, this group is sometimes called an ethyl group, and it can be abbreviated as ET, and we can focus on the oxygen this way because there's 2 lone pairs of electrons. It's bent about the oxygen. With an approximately 109.5 degree angle of the carbon to oxygen to hydrogen angle. Why is it 109.5? Because there's 4 groups of electrons, 1, 2, 3, 4. The way that 4 groups of electrons get as far apart from each other as possible in space is with a tetrahedral orientation, which is 109.5. This is not a perfectly symmetric shape, so it's polar. Furthermore, this is partial plus, partial minus. This is a polarized hydrogen, which will hydrogen bond to the oxygen of another ethanol molecule. That hydrogen bond looks like this. Here's an oxygen of another ethanol molecule. And this, what I've drawn as a dashed line, this represents an H bond. I don't like the term hydrogen bond because bond sounds like a covalent bond. A hydrogen bond is an intermolecular attraction between 2 separate molecules. So it's an intermolecular attraction between 2 different molecules. It's not a bond inside of a molecule. So ethanol has hydrogen bonding. It's a polar molecule, so it also has dipole-dipole. And as all substances have, it has London dispersion forces. So that's got all 3. Now, when we look at the next one, I'm not going to draw out the complete Lewis structure like I did here where I draw everything out, but you can see there's a CH3CH2O, just like we had CH3CH2O. We can call that an ethyl group. So you could think of this way as an ethyl group over here, an ethyl group over here. There's 2 lone pairs of electrons. There's 4 groups of electrons around that oxygen. So the carbon-oxygen-carbon bond angle is approximately 109.5. This is bent approximately 109.5 degrees. Why 109.5? Because there's 4 groups of electrons around that oxygen, which is polar. However, this does not have any polarized hydrogens. It does have oxygen and it has hydrogens. But in order to have hydrogen bonding, you have to have a polarized hydrogen. Remember what I mean by a polarized hydrogen. A polarized hydrogen is a hydrogen covalently attached inside of a molecule to either fluorine, oxygen, or nitrogen. There is no hydrogen covalently attached to this oxygen. It's polar. It does not do hydrogen bonding. It does have dipole-dipole forces, because it's a polar molecule, it's not perfectly symmetric, and it's got London dispersion forces. Next, we'll look at the molecule carbon dioxide. So when we look at the molecule of carbon dioxide, now the shortcut for drawing the Lewis structure, carbon generally has 4 bonds, each oxygen has 2 bonds. So how can we give carbon 4 bonds and each oxygen 2 bonds? If we have carbon in the middle, doubly bonded to each oxygen. And anytime oxygen has 2 bonds, there'll be 2 lone pairs on it. Now, since there are 2 groups of electrons, this double bond is 1 group of electrons, this double bond is 1 group of electrons. They want to get as far apart from each other as possible, and therefore this molecule is going to be linear 180 degrees. This is linear 180 degrees. Oxygen is more electronegative than carbon, so there's a partial negative here. The carbon's partial positive, but here this oxygen's partial negative too. And you can see that the center of negative charge is right dead center in the middle of the molecule where carbon is, and that's where the center of positive charge is. If the center of negative charge is in the same spot as the center of positive charge, then it is a nonpolar molecule. Another way to look at this is that this linear molecule is perfectly symmetric, so it's nonpolar. Since it's nonpolar, the only type of intermolecular force present will be London dispersion forces. London dispersion forces. This next molecule is called trimethylamine. Nitrogen is attached to 3 CH3 groups. Nitrogen typically has 3 bonds and a lone pair of electrons. And so if nitrogen has 3 single bonds and a lone pair of electrons, there will be 4 electron groups around it, which we can jump ahead and picture that as this, with a CH3 in the plane of the paper. Here's a wedge coming out toward us, a CH3, and here's a CH3 going down and back. Now there's a lone pair of electrons up here. That would be, if you count that lone pair of electrons, that looks tetrahedral. And the shape of the molecule from the perspective of the nitrogen is a trigonal pyramid, trigonal pyramidal. And this is trigonal pyramidal about the nitrogen. The angles are approximately 109.5 degrees. Why approximately 109.5? Because we have 4 groups of electrons. 1, 2, 3, 4. This is not one of the perfectly symmetric shapes. Therefore, this is polar. And since this is a polar molecule, this molecule has 2 types of intermolecular attractions. It's got dipole-dipole forces, and it's got London dispersion forces. But if I replace one of these CH3s with a hydrogen, so let's put a hydrogen here. Now, at this wedge coming out of the plane of the paper toward us is the other CH3. Here's the CH3 going back. There's a lone pair of electrons. Now, this is a polarized hydrogen. It's a hydrogen attached to inside of a molecule of very electronegative fluorine, oxygen, or nitrogen. This is a polarized hydrogen. And it will hydrogen bond to a nitrogen of another molecule of CH3-2NH. This is a very electronegative nitrogen right here, partial negative. And so this attraction between a polarized hydrogen on one molecule and a very electronegative atom on another is called a hydrogen bond. If this is a polar molecule, but it also has hydrogen bonds. So the types of intermolecular attractive forces here will be, it has hydrogen bonds, dipole-dipole forces, and London dispersion forces. All 3. This last molecule is one that we talked about in class. This is ethylene glycol, which is present in antifreeze. Ethylene glycol present in antifreeze. And you'll see, as I have these, I can draw this out this way, a CH2, there's an OH and an OH, and I have a polarized hydrogen. This is not a perfectly symmetric molecule. It's polar, and it has hydrogen bonds. Because I've got a polarized hydrogen attached to a very electronegative oxygen. So this will have lots of hydrogen bonds, and so the types of intermolecular attractive forces for this will be hydrogen bonds, dipole-dipole forces, and London dispersion forces. Okay, so to determine the types of intermolecular attractive forces, you have to know the shape of the molecules. That's what question number 1 was trying to illustrate. Question number 2 asks you to compare a series of molecules and predict which has the stronger intermolecular forces. So remember, the stronger the intermolecular force, the higher the boiling point. The stronger the intermolecular force, the higher the boiling point. Now, you have to understand what these molecules are, how the atoms are attached in this case. And it will help you remember that carbon has 4 bonds. In my organic chemistry class, my students wake up screaming that carbon has 4 bonds. So this first molecule, CH3, it's tetrahedral about this carbon because it's got 4 single bonds. This CH3 is attached to the carbon that follows. Now, what is this carbon attached to in order for it to have 4 bonds? Well, it's attached to the carbon in front. It's attached to a hydrogen, so it must be doubly bonded to an oxygen. That gives oxygen 2 bonds. It gives each hydrogen 1 bond, each carbon 4 bonds. This carbon has 4 bonds, 1, 2, 3, 4. Notice this does not have hydrogen bonds. This is polar, but it does not hydrogen bond to itself because it does not have a hydrogen covalently attached to oxygen inside of the molecule. You have to look at the formula and know that hydrogen is not attached to the oxygen. The hydrogen is attached to the carbon, so it's not polarized. And so this only has dipole-dipole forces. In contrast to that, ethanol, CH3, CH2, OH, this has hydrogen bonds. If you are comparing small molecules of similar size, and these 2 molecules are similar in size, if you're comparing small molecules of similar size, hydrogen bonds are the strongest intermolecular attractions, and therefore the answer to this is that ethanol, CH3, CH2, OH, has the higher boiling point. That of these 2 molecules, it's ethanol that has the higher boiling point. The answer is ethanol because of hydrogen bonds. Okay, well, let's look at B then, which is the higher boiling point. Now, both of these have hydrogen bonds. They both have hydrogen bonds. But since both have hydrogen bonds, then we have to determine, which one has the stronger London dispersion forces? Well, CH3, CH2OH is larger, and so it has greater London dispersion forces. The larger the molecule, the greater the London dispersion forces. And therefore, since there's more atoms here, you're comparing apples to apples because they both have hydrogen bonds, but this has more atoms, it's larger, and so therefore this has the higher boiling point. Ethanol has a higher boiling point than the first molecule, which is methanol. We'll circle this one. Okay, and the next question, choice C, which has the higher boiling point, sodium chloride or PCl3? Well, right off the bat, NaCl, that's a metal and a nonmetal, and it is an ionic compound. Whereas PCl3 is 2 nonmetals. This is a covalent compound. And ionic compounds, compared to covalent compounds, usually always have much higher boiling points. So the answer in this case is sodium chloride. Sodium chloride, being an ionic compound, has a much higher boiling point. And actually, the melting point, I don't even know what the boiling point is, the melting point, this is a solid at room temperature, is 801 degrees C. That's what it takes to melt it, to go from the solid to the liquid. To boil it, it would be much higher than this. PCl3, though, is a gas at room temperature. PCl3 is a gas at room temperature. So that shows that PCl3, which is a covalent compound, has a much lower boiling point than sodium chloride. Now, you don't have to determine which molecule is more polar. You just need to know if something is polar or not. So when you're comparing these compounds, what you should know, this first compound is a hydrocarbon. And what do we know about hydrocarbons? They are essentially nonpolar. The rest of these compounds are not hydrocarbons. They're polar. Now, in this compound right here, or this column right here, this is the Greek letter mu, which stands for the dipole moment. Dipole moment. The capital D is the unit. It's the debye. It's in units of debye. And so this is a measure of how polar the molecule is. A measure of how polar the molecule is. And so as you look at this, the most polar molecule, they're all similar in size. The reason this second column is here, this is the molar mass, and they're similar in size. So we're comparing apples to apples. They're all similar in size, but the last one is much more polar, has a much higher dipole moment, and therefore this has the highest boiling point of the ones listed. And this one, which is essentially nonpolar, this has the lowest boiling point, because the only type of intermolecular attraction present in this first molecule is London dispersion forces. Okay, let's go to the next page and look at question number 4. Okay. So on question number 4. This is a plot of the vapor pressure of several substances versus temperature. Now, first of all, you need to know what vapor pressure is. Vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid or solid state. So, for example, if it's water, if I have liquid water in equilibrium with water in the gas phase, I call this water vapor. It's called water vapor when it's in the gas phase because the most stable form of water at room temperature and pressure would be as a liquid. And the pressure exerted by this vapor is called the vapor pressure. And 2 points. One, at higher temperatures, the vapor pressure of a substance increases. The vapor pressure of a substance increases. And that's what you see right here. If you focus on water, the vapor pressure is very low here, but it increases as you increase the temperature. Okay? And the next point is that the boiling point is the temperature at which the vapor pressure equals the external pressure. Now, if the external pressure is 1 atmosphere, that's called the normal boiling point. The normal boiling point is the temperature at which the vapor pressure equals 1 atmosphere. The temperature at which the vapor pressure equals 1 atmosphere. Okay, so that if you look at the vapor pressure here in torr, now 1 atmosphere in torr is 760 torr. So if this is 600, if this is 700, then 760 would be right about here. So if I just draw this dashed line, we're just going to eyeball this, then this asks what's the normal boiling point. Normal boiling point means the boiling point at the temperature at which the vapor pressure equals 760, which would be right about here. So if we come down here, it's very close to 60 degrees C. So the correct answer is 60 degrees C. You can see that water has a boiling point at 760 torr of 100. The boiling point of carbon tetrachloride right here. Looks like it's just a little below 80 degrees C is the normal boiling point. Okay, one of the questions that you need to be prepared for on the exam would be to determine, looking at a particular substance, what are the strongest intermolecular forces holding them together. So hydrogen iodide, let's draw the structure of hydrogen iodide. Hydrogen is covalently attached to iodine. That's the Lewis structure. Iodine is a halogen. It's more electronegative than hydrogen. So this is a polar molecule. A polar molecule. So we know that it has dipole-dipole. Therefore, it has dipole-dipole forces. And the question is, does it have hydrogen bonds? Does it have hydrogen bonds? Now, it's got this hydrogen that's a partial positive, and I have an electronegative iodine, but the answer is no. It does not have hydrogen bonds. Instead, this just be a dipole-dipole attraction. If I were to draw what that looks like, here's one molecule of hydrogen iodide, and the positive end of one molecule is attracted to the negative end of another molecule of hydrogen iodide. So partial plus, partial minus, partial plus, partial minus. In this case, this is not called a hydrogen bond. This is called a dipole-dipole force. It's not a hydrogen bond because the definition of a hydrogen bond is if you have a polarized hydrogen, which is where you have hydrogen covalently attached to fluorine, or covalently attached inside of a molecule to oxygen, or covalently attached inside of a molecule to nitrogen. Those are the only three kinds of hydrogens that can hydrogen bond. A hydrogen covalently attached to fluorine, oxygen, or nitrogen. And it can hydrogen bond to another atom of either fluorine, oxygen, or nitrogen on another molecule. So this doesn't have fluorine, oxygen, or nitrogen. It's polar. It has dipole-dipole forces. It also has London dispersion forces. But in small molecules, dipole-dipole forces are stronger than London dispersion forces. And so the correct answer, number 5, is choice A. Question number 6. Select the pair of substances in which the one with the higher vapor pressure at a given temperature is listed first. Okay, now what you need to know here, if this says the highest vapor pressure, then what do we have to know about the intermolecular forces? And so the key to knowing this is that the stronger the intermolecular force, the stronger the intermolecular force, the what, the vapor pressure, the higher or the lower, the what, the vapor pressure. Well, since the vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid or solid state, and here's the picture that we drew in class. I have an enclosed container. Here's a pressure gauge. You know, I have some liquid in here. The only gas in here is the evaporated molecules in here. So we don't have any air or any other molecules, just whatever this, if this is water, the only gas particles up here are water. And there will be an equilibrium between the liquid and the gas phase. Okay. Well, the stronger the intermolecular attractive force is, the more the molecules are held together in the liquid phase. And so the lower the vapor pressure, the lower the vapor pressure. The stronger the intermolecular force is, the lower the vapor pressure. So when this says comparing two at a time, which has the higher vapor pressure, which one has the higher vapor pressure listed first, then that means we need the one with the weakest intermolecular force listed first, the weakest intermolecular force first. So we're going to compare just two at a time. In A, I'm comparing two hydrocarbons, the only types of intermolecular attractions present in hydrocarbons since they are nonpolar or London dispersion forces. But this is bigger. It has stronger London dispersion forces. So this has stronger forces. So this molecule with stronger forces has the lower vapor pressure. Remember, the stronger the intermolecular force, the lower the vapor pressure. So it can't be A. In this case, we have two molecules that are both tetrahedral. Here's CCl4. It's tetrahedral. And here's CBr4. It's also tetrahedral. They're both nonpolar. But between them, which one of those has stronger? Well, they're both nonpolar, so it has only London dispersion forces. And so as we look at the periodic table, here's chlorine and bromine. CBr4 is bigger than CCl4 because bromine is bigger than chlorine. And therefore, CBr4 has stronger intermolecular forces. And so as we look at this, CCl4 has weaker intermolecular forces. This is smaller. So B is the correct answer. This has weaker forces, so it has a higher vapor pressure than CBr4. Now let's go ahead and finish them. We know that B is the answer, but as I look at C, in both cases these are bent molecules. So here's water is bent, it's polar, and H2S is bent and polar. Sulfur is right underneath oxygen on the periodic table, and so the shapes of the molecules are similar. But H2O, even though it's smaller, it has hydrogen bonds. So hydrogen bonds are stronger, and water is less less volatile. It has a lower vapor pressure because hydrogen bonds are stronger, so it can't be C. Then between these two, ethanol has hydrogen bonding. Dimethyl ether does not have hydrogen bonding. There's no hydrogen attached to the oxygen in this molecule, so it does not hydrogen bond to itself. Hydrogen bonding is stronger than dipole-dipole forces, and so this has a lower vapor pressure, so it's not D. Between xenon and krypton, those are both noble gases. As we look on the periodic table, xenon is bigger, and so it has stronger London dispersion forces than krypton. It has stronger London forces, so it has a lower vapor pressure, and that's why that's not the answer. So B is the answer. Number 7, as we compare these molecules, each of these molecules consists of carbon with 4 atoms, I'll just call them X, situated about the carbon in a tetrahedral fashion. Tetrahedral is perfectly symmetric, tetrahedral, perfectly symmetric, so therefore each of these are nonpolar. Since they are all nonpolar, how can we determine which of these has the highest boiling point? Well, the only types of intermolecular attractions are London forces, and London forces increase with increasing size. Now, one way that we can estimate the size is with the molar mass. So using the periodic table, the molar mass of methane is 16 grams per mole. For CF4, the molar mass is 35 grams per mole. Now, what we're doing, we don't even have to calculate these because I've got fluorine, chlorine, bromine, and iodine. You can see we're going down the periodic table. Fluorine, chlorine, bromine, iodine, they're getting bigger. I'll go ahead and write the molar mass of each one. The molar mass of carbon tetrachloride is 154 grams per mole. Carbon tetrabromide, well, I did not jot that down, so I don't remember this, and I may have missed one here, but this is CI4. In this font, it might look like chlorine, but it's CI4. And CI4 has a molar mass of 520. This is by far the largest. You don't even need to calculate the molar mass because when we look on the periodic table, they're all tetrahedral with fluorine, chlorine, bromine, and iodine. That's the biggest, so that has the strongest London dispersion forces. It's the highest boiling point. Now, if I were to ask which of these has the lowest boiling point, that would be a fair question. Then A, this has the lowest of the ones listed boiling point because it's smallest. Okay, one of the things that you need to do for this exam is to be able to interpret these line drawings so that you can understand some simple organic molecules. And the way that line drawings work is that you show carbon-carbon bonds. You show carbon-carbon bonds. So if you see a line, that's a carbon-carbon bond, but carbon and hydrogen are not shown most of the time. I should say they are usually not shown. We will see some cases where they are shown, and I'll explain that. Okay, so as I look at this molecule, this is saying that this is a carbon-carbon bond. So there's a carbon here and a carbon here. There's a carbon here and a carbon here. And then around this ring, everywhere lines come together, there's a carbon. There's a carbon here, 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 and here. So those are the carbons. And so as I count the carbons, this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is C10. But there are also hydrogens. Now, how do I know how many hydrogens? I know how many hydrogens. I mentally supply the hydrogens knowing that carbon has 4 bonds. So that'll be the next bullet point here. each carbon has 4 bonds. So you supply enough hydrogens to give each carbon the 4 bonds that it needs to satisfy its valence. So for example, this carbon, I see 1 bond, so there must be 3 hydrogens here. This carbon, I see 2 bonds, so there must be 2 hydrogens here. This carbon, I just see 1 bond. This has 3 hydrogens. Here I see 2. This is 2 hydrogens. That gives this carbon 4 bonds. Now for this carbon, how many bonds do I see? I see 1, 2, 3, so there's 1 hydrogen. This carbon, how many bonds do I see? I see 1, 2, 3, 4. This carbon already has 4 bonds, no hydrogens. How many hydrogens does this carbon have? 1, 2, 3, so it's got another one. How about this one? How many hydrogens does it have? 1, 2, 3 bonds, so it's got 1 hydrogen. This carbon has 1, 2, 3 bonds. It's got 1 hydrogen. So those are the hydrogens. Let's add them up. 3 plus 2 is 5. 6, 7, 8, 9, plus 2 is 11, plus 3 is 14. So C10H14, that's the molecular formula of this compound. Okay. Let's do the next one. Now, if the line goes to another element, I said that it shows the carbon-carbon bonds, but carbon's not written. If the line goes to another element, this is a bond from a carbon to that element. So here's a carbon, and here's a carbon, but this line is from the carbon to the oxygen. So there's not 3 carbons here, there's just 2. Here's a carbon, and there's not a carbon right here. This is a bond between carbon and oxygen. Now I wake up screaming that carbon has 4 bonds. This carbon I see 1 bond, so there must be 3 hydrogens. This carbon I see 2 bonds, so there must be 2 hydrogens. This carbon has 1 bond, there's 3 hydrogens. This carbon I see 2 bonds, there must be 2 hydrogens. So this is going to be C, 1, 2, 3, 4, C4, H, and 3 plus 2 is 5, plus 2 is 7, plus 3 is 10, O. Now, you won't be expected to know this on the exam. I will point out that the rule of thumb, the order for writing the letters is we write carbon first, then hydrogen, then any other elements we put in alphabetical order afterwards. Okay, so look at the next molecule. How many carbons, hydrogens? We don't have any other elements, just carbon and hydrogen. This is a hydrocarbon here. And so there's a carbon anywhere the lines come together. Now we wake up screaming carbon has 4 bonds, and we mentally supply enough hydrogens to give each carbon 4 bonds. Well, this carbon has 2 bonds, there must be 2 hydrogens. This carbon has 3 bonds, there must be 1 hydrogen. This carbon has 3 bonds, there must be 1 hydrogen. This carbon has 2 bonds, there's 2 hydrogens, 2 hydrogens, 2 hydrogens. And so this is C6. There's 6 carbons in the ring. 1, 2, 3, 4, 5, 6. H, and now when we count these, I've got 2, 4, 6, 8, 10. C6 H10 is the structure, is the molecular formula for this compound. So be sure you can determine the molecular formula for one of these line drawings. You also need to know some of the important organic functional groups. I went over them in class, and they're also listed in a table in your book. So this is what gives these molecules their characteristic behavior. Now notice in this molecule we have a carbon right here attached to a carbon, doubly bonded to an oxygen, attached to an oxygen, attached to another carbon. That's a carbon right here. And when you see that, a carbon doubly bonded to an oxygen and an oxygen here, and a carbon on either side, this is an ester. This is an ester. So the functional group present in this molecule is an ester functional group. Now, anytime you have an OH in an organic molecule, that makes it an alcohol. So if you have a carbon attached to an OH, that makes it an alcohol. You know, so for example, ethanol, CH3, CH2, OH is ethanol. Ethanol is the type of alcohol present in alcoholic beverages. So that's ethanol, it's an alcohol. This is an alcohol. As I look at this molecule, in this case, we have, just focusing on this part, this is the functional group of the molecule that we're focused on. I'll have a C double bond O, it's attached to another C over here, attached to a nitrogen with a hydrogen, attached to another C over here. And this much, where I have a carbon attached to a nitrogen and doubly bonded to an oxygen, this is called an amide. An amide. Some people pronounce it an amide, and that's okay to call it an amide. So an ester, an alcohol, an amide. The next three kinds of carbons. Notice that in all three of these, there are only carbons and hydrogens. So each of these are hydrocarbons. This is hydrocarbon. This is a hydrocarbon. And this is also a hydrocarbon, because the only elements present are carbon and hydrogen. However, as we look at these, the one in the middle, all of these are all of the carbon-carbon bonds are single bonds. And therefore, this is an alkane. An alkane. Alkanes have all the bonds are carbon-carbon single bonds. If you have a carbon-carbon double bond, that's an alkene. An alkene. So right here is an alkene, because an alkene has at least one carbon-carbon double bond. At least one carbon-carbon double bond. Okay. And then this last case is an alkyne. This is an alkyne. In an alkyne, there's at least one carbon-carbon triple bond. An alkyne has at least one carbon-carbon triple bond. So an alkane has all carbon-carbon single bonds. An alkene has at least one carbon-carbon double bond. An alkyne has at least one carbon-carbon triple bond. So that's the functional group present in those molecules. Okay, now we're going to shift over and talk about unit cells and polymers. And we will do that in the next problem session.